Welcome again. Today, we will talk about one of the most important network models which has a vast application in project management. The method is known as the critical path method, or CPM. This method is used when the duration of the activities is known with certainty. If this is not the case, then the recommendation is to use the Program Evaluation Review Technique method. In this talk, we will only address the critical path method. You may be asking yourself the question, what do network models have to do with project management? Let me take a few moments to explain the relationship between these two concepts. Today, we are in one of Garmont's companies called GEM Constructions. This part of Garmont is dedicated to building houses with innovative materials. To build a house, we regularly have to perform several tasks. The task description, its duration, and the predecessors of each task, are shown in the following table. In this case, a predecessor of an activity is a task that has to be done before the activity can be started. For instance, we cannot build a wall without having finished the foundation. This set of tasks can be represented as a network. Observe this figure. The objective of the figure is to graphically represent the set of activities and the sequence in which they must be performed. The first step is to do activity A, and only when this activity is done, we can do activity B. When B is finished, we can do activities C and D. When D is done, we can perform activity E. And when E is finished, we can perform activity F. And when this is done, we can perform activity G. But we can only perform activity H, until C and G are finished. The arc that joins node 4 with node 8, is called a dummy activity. And its objective is to indicate that to start activity H, besides finishing G, it is also necessary to finish activity C. The arc that joins nodes 9 and 10, is also a dummy activity, and it is used to indicate that to finish the whole project, it is necessary to finish activities H and I. As you can see, projects can also be presented as a network. Now, when we have a critical path problem, we usually want to know the duration of the project, and the activities that cannot be delayed. To do this, we will define the following variables. Xi represents the start date of activity X. And Xf represents the finish date of activity X. Usually we want to know the earliest finished date of the project. As you can see in the network, the project will end when the activities H and I are finished. You can also deduce this from the table. If you search for the activities which do not precede any other activity, you can select any of them, and with it, construct the objective function. I will select activity I, and the objective function will be to minimize IF. I invite you to observe carefully the constraints. The constraints we will indicate are called start constraints. What we can say about the first constraint, is that the start date of activity B, must occur after the finish date of activity A. This constraint is due to the fact that, activity A precedes activity B. Similarly, observe that activity C can only start until activity B is finished. Activity D can start only until activity C finishes, and similarly for the remaining activities. I ask to observe specially activity H, which has two predecessors. In this case, H starts until both predecessors are finished. Now we will consider the constraints for the finish time of the activities. I ask you again to observe carefully the following set of constraints. The first constraint indicates that activity A will end 5 time units after it started, since that is the duration of the activity. And the same will happen with the remaining activities. We only need to indicate one more constraint. Given that both activities, H and I, must be finished in order to finish the project, and that activity I was selected as finish date. We must make sure that by that date, activity H is also finished. We achieve this with the following constraint. Now we will run the model in the software, and the following results will be obtained. As you can see, the project could be finished in 34 days. Now, let me add the duration of the activities to the network. As you can see, we can travel from node A to node B in 5 days, and if we continue traveling with no delays, we could get from node 1 to node 3 in 13 days. If we continue doing this, starting an activity as soon as its predecessor is finished, we will obtain the following. Now, it should be very clear that we can finish the project in 34 days. But in addition, if you observe the diagram carefully, you will realize that there is a set of activities that cannot be delayed, since otherwise the project would not be completed in 34 days. In this example, those activities are A, B, D, E, F, G and H. This set of activities is called the critical path. Activities C and I could have some slack, but we must make sure that the activities in the critical path are not delayed. There is a more interesting problem associated with the critical path. This problem is called critical path with crash times. For instance, suppose that for the previous example we have promised our customer to finish the project in 30 days. This means that the duration of the project must be reduced by 4 days. Let me erase everything and I will show you the table with 3 more columns. Now suppose that we have made an investigation to find out which activities can be done faster. This will usually cost more. For instance, activity A can usually be done in 5 days, but working overtime and leasing a more efficient equipment, it could be done in 3 days. But this implies that the normal cost of $5,000 will increase to $7,500. The last column indicates the cost for each day that the activity is crashed. In the case of activity A, the additional cost is $2,500, and it will be finished 2 days earlier. This means that the cost of each day of reduction represents a cost of $1,250. In the case of activity B, the additional cost is $1,500 for each saved day. Consider that in activities F and I, this unit cost cannot be computed, since none of these activities can be crashed. I will present a new table which includes these values. Besides, it is important to observe that the sum of the costs when normal times are considered is $58,000. Usually, in these cases we want to minimize the cost of the project, assuming that the project is finished before the established date, which in this case is 30 days. The normal costs can be considered as fixed costs. What we need to minimize is the cost incurred for crashing some activities. Now we will define 3 types of variables. Let xi the starting date of activity X, xf the finish date of activity X, and xc the number of days activity X is crashed. Our objective function must reflect the extra payment we have to make, and therefore the expression which represents this intention is the following. This objective function must be subject to the following constraints. The start constraints are the same as before. But in the finish constraints, we must now take into account the time the activity can be crashed. For instance, in activity A, its finish time must be equal to the start time plus the duration of the activity. But now we must subtract the crash time. Similarly, as we did for activity A, we must do the same for all the activities that can be crashed. Observe that for activities F and I, the crash time is not subtracted, since these activities cannot be crashed. Now we need to add the crash time constraints. Those constraints indicate the maximum number of days that each activity can be crashed. I believe that these constraints are fairly easy to comprehend. For instance, activity A can be crashed from 5 to 3 days, which tells us that the maximum number of crash days is 2, and for this reason, we indicate AC less than or equal to 2. Finally, we only need to make sure that the project will be finished in 30 days or less. As we mentioned, the project ends when activities H and I are finished. Therefore, we will add these two constraints. When the model is run with the software, we obtain the following results. The most important part to consider is which activities must be crashed. In this case, activity A is crashed 1 day, activity G 2 days, and activity H 1 day. And this will generate an additional cost of $4,450, which means that we will invest $62,450 in the project. $58,000 was the fixed cost for the normal activities, and $4,450 for the extra effort to finish in 30 days. Now, suppose that the calculated cost seems to be too high, and that the most we are willing to spend in a construction is $60,000. Now, the relevant question is, what is the smallest time in which we can deliver a house to our customers? This problem does not imply a lot of effort to be solved. Again, we want to minimize the construction time, and the objective function is to minimize IF. That is to say, we discard the current objective function and substitute it with this. We also discard the two last constraints which ensured that the project would be finished in 30 days or less, and substitute them with the constraint that ensures that the finished time of activity H will be less than or equal to the finished time of activity I. Finally, recall that we do not wish to spend more than $60,000 in each house, and therefore, we only have $2,000 to crash the activities. This will be expressed with the following constraint. Moreover, all the start, finish, and crash constraints must remain. I will run the model in the software, and this will be the new solution. The new solution indicates that we only need to decrease the duration of activity G by 2 days, and the project can be finished in 32 days. As you can see, the critical path method has a lot to do with project management. I thank you again for your company. I'll see you soon.